So today's discussion is going to be on duality, mainly KKT conditions. So the problems themselves are pretty simple, but what we want to focus on in this particular version of discussion is interaction. So we want to work together and help each other find the answers. The lecture version of this discussion will be posted. The recorded version of this will be posted on the website. So Theo has already done it. So in this interactive discussion, we are not going to be able to cover the entire sheet because we will take some time to do breakout rooms and talk to each other. So we won't be going that fast, but you can rest assured that the entire discussion will be covered by Theo and posted online. Is that clear?
Yep.
Okay, great. So let's begin with the first problem. So this problem considers the objective function. Okay, I can point it out like this. This is the objective function, x squared. If you want to draw this, you can draw this on your axis. X squared. This is my x. This is my f of x. And here you have the constraints. X greater than equal to 1 and x less than equal to 2. So let me change my color. So this is the region, x greater than equal to 1, x less than equal to 2. So this is the feasible region. Yeah, and the objective is to minimize x squared subject to these constraints. So for the first part, we first want to figure out a couple of things about this problem. First, is the problem convex? Second, does latest condition hold? And third, does strong duality hold? So now, since there are just few of us, I think it's not necessary to do breakout rooms. So we can all use just the main room. So why don't you discuss among each other and come up with answers to this? So if you have any doubts, feel free to ask me. So you can also share your paper, photo of your paper for your work, or if you're using an iPad, you can share a screen. You can also unmute yourself and talk. Yeah, but the goal of this discussion was to encourage this interaction. So let's do that starting from the first part. So do you have any questions about these concepts? Like, what do you mean by problem convex? What is latest condition? Is this clear to everyone?
Could you quickly go over Slater's condition again?
Okay, sure. So Slater's condition. So that's the hard version and the easy version. Easy version is what you would require for this course. So you want a strictly feasible point. So what does that mean? So you want a feasible point in the interior. For this course, it's sufficient to just interior of your feasible region. Okay, so what it says is you should have at least one point that lies in the interior of your feasible region. So there are multiple ways to interpret this. So if you want to think about it as a set, so I will think about a set in one dimension. So your set in one dimension is just going to be an interval. So if you have something like this, so which is what we have, okay, let's say 0 to 1, and this is your entire feasible region. Then you have points which lie inside the feasible region. So for example, 0.25 lies inside the feasible region, 0.75 lies inside feasible region, so on. So both these points are strictly feasible points. Okay, this is a set interpretation. However, if your feasible set was just 1 point, let's say your entire feasible set is just the point 0. So how would you get something like this? You would get something like this if you had a constraint. For example, minimize f of x subject
sorry,
to.
I think you are muted.
Am I muted?
No, I can hear.
Okay. So who is having audio problems? Can you check your audio?
Can't hear you.
Laura, can you ask this person if their audio is muted?
Yeah, I
So-
can add stuff through the chat.
Okay, sure. Okay, so this, for example, if you like minimize f of x subject to x square less than equal to 0, so such a constraint would lead to only one feasible point, 0. So in this case, you don't have any feasible point in the interior of the feasible region. So is that clear now? What do you mean by feasible point interior of feasible region?
Yes.
Yeah.
Okay, so the hard definition uses like relative interior, but for this course, we won't need the difference between relative interior and interior. Okay, so why don't you discuss and solve this part now?
Okay. So for this one, well, I mean, the feasible region is when x squared is from between 1 and 2.
Mm-hmm.
Wait, what does it mean if it like Slater condition holds?
Just ask you to see if there is a strictly feasible point.
If there is a strictly. So I'm confused because like let's say like we didn't have those constraints, then the answer, the x star would be 0, right?
Yeah.
But since we're constrained to the region 1 and 2, does that tell us something? Because like x star is not inside of this region.
Yeah, but
Does that mean?
the thing is, since you have this constraint, your x star is different now, right? So your x star
Yeah.
for the unconstrained problem was 0, but for your constrained
Yeah.
problem, it's something else.
Okay, yeah. So for the constraint problem, it should be 1, but
Yes, it's going to be
I
1,
don't-
which we'll
I'm just confused,
arrive
like-
at later. But for
Uh-huh.
latest conditions, we only want to see feasible points, like what x lie within my constraint set. So we just don't care about the optimal for latest condition, we care about feasible points.
Okay, so just to clarify, we're when we're trying to figure out if Slater's condition holds, we only have to look at like the set of points and we can ignore the objective function. Is that true?
Yes, for latest condition, yes. So you just want to
Okay.
look at the constraints. Yeah.
Okay.
So, but that brings up an interesting question, like when is latest condition useful? So it's useful to say something only if your problem is convex, which is like the second part of this part A. And to figure out whether a problem is convex, you have to look at the objective function.
Yeah.
So is that clear?
I have another question on the Slater condition. So for the interior point, what's the definition of interior point? So it doesn't, if our set is just one point on the real line, then we don't consider that interior, right?
Yes,
Or
we don't
if
consider
the
that
set is
interior.
discrete, then there's no interior point.
Yes, there is no interior point.
Okay, thank you.
Okay, so for ours, does latest condition hold?
I guess,
Yes.
yeah.
Okay. Why? What is the feasible region?
1 to 2.
Okay, great. So answers, I'll show the answers later, so I'm not going to write them down. Yeah, but it's good for you to write it down. So what about the second part? Like, how do you check if a problem is convex?
Okay, yeah, we can use that. We can use Jensen's inequality. So like we draw a chord and show that the points on the x squared are all below the chord.
So you want to check if for problem convex, you need to check if objective is convex. If it's a minimization problem, so objective, if minimization problem convex, you want to check first if objective is convex. Second, you want to check if inequality constraints are convex. And finally, you want to check if equality constraints are affine. Okay, so in general, if you want to check if a problem is convex and it's a minimization problem, this is what you have to check. So is the objective function convex? like someone mentioned, it is convex because you can do it by definition, like odds lie above the function, or you can also just take second derivative and see second derivative is 2, which is greater than 0. So what are the inequality constraints here? So inequality constraints, x greater than or equal to 1. Is this, so when you want to check inequality constraints, you should always convert it into a form less than or equal to 0. You want to write this as minus x plus 1 less than or equal to 0, and then you will check if this function is convex. So this, let's say, is your f1 of x equal to minus x plus 1. So is f1 of x convex?
Yes.
Yes, because it's affine, so it is convex. Similarly, for this, you write it as x minus 2 less than or equal to 0. And x minus 2 is again convex because it's affine. So is that clear now?
Yeah.
Okay, so final part, does strong duality hold? So you only use the previous two answers, right?
Yeah, so since Slater's condition holds and the problem is convex, I think that's like we can conclude strong duality holds, right?
Yes, exactly. So that's the main use of Slater's condition. It's used along with the problem being convex to argue that strong duality holds. Okay, great. So this is the solution. So we have strictly feasible point, x is 1.5, that lies in the relative interior, blah, blah, blah. Objective function x squared is convex, and inequality constraints are affine and thus convex. The problem is convex. That's again what we saw. Since Slater's conditions hold and problem is convex, strong duality holds. Okay, great. So let's go to part B. So you want to write the Lagrangian L of x lambda 1 lambda 2. So for this, I'm going to scroll back to this objective function. So again, feel free to discuss and write the Lagrangian. So this should be something you have seen several times before. So hopefully you're all comfortable with doing this. L of x lambda 1 lambda 2. So why don't you take a minute and figure out how to find the Lagrangian. Yeah, feel free to discuss, show work. Anyone?
But do you want to just like give the answer or?
Yeah, for this
what do
part,
you
you can just share your work. Yeah, because there's not much to discuss, right?
Yeah. So for this one, the Lagrange is like f naught of x plus lambda 1 times f1 of x plus lambda 2 times f2 of x, and then we defined f1 of x and f2 of x above, like we wrote the inequality.
Okay, great. So can everyone read this?
Yeah.
This part.
Yes.
So this is your f naught of x objective function. This is your lambda 1 times f1 of x. And this is lambda 2 times f2 of x. Okay. So now that we have the Lagrangian, we want to solve the KKT conditions. But what are the KKT conditions? Can like everyone help me with writing like different things to check for KKT conditions? So let me like start out with the first heading. So I want stationarity. What is the stationarity condition of KKT? Can someone help me with that? So you have seen KKT before, right?
Yeah.
It means X star minimizes the Lagrangian, given we substituted lambda 1 star and lambda 2 star into the Lagrangian.
So how do you write it down, like in terms of vector calculus?
We can say the gradient, or in this case,
So derivative,
yeah,
depending on the
derivative
gradient,
of
yeah.
Lagrangian with x equals x star equals 0.
This is the condition, right? And what is the gradient with respect to?
To x.
And show it only with respect to x. So you can check. Yep. So the thing here is you will take the derivative of gradient with respect to x, but then you will substitute your optimal lambdas. But when you like solve it, it will become clear. So this is just notation. So in general, you don't have to put these stars when you solve it. You can just put x, lambda, and nu. But it turns out that this, if something satisfies KKT, then it will be the optimum. That's why you are putting these stars here, like x star, lambda star. So is that clear? Like, why are we putting the stars here?
Yeah.
Okay. So what's the next condition? I'll help you with this title, feasibility. So what do you want?
X star
our
is
problem?
primo feasible.
Yeah. So let's just write it for our problem now. So you want x star greater than equal to 1, x star less than equal to 2. Is this clear why? Like primal feasibility.
Yeah.
And coming back to this, or let's finish dual feasibility. What is dual feasibility for us?
We have the lambda 1 and lambda 2 are both greater than or equal to 0.
Yep, lambda 1 star greater than equal to 0, lambda 2 star. So what is stationarity condition for us? What was our function? What was the Lagrangian? It's here. So what happens when I take the derivative with respect to x? What do I get? I get 2x plus lambda 1 times minus 1 plus lambda 2 times minus 1, no, plus 1 equal to 0. So that implies 2x minus lambda 1 plus lambda 2 equal to 0. Okay. So what is the other most important KKT condition? Complementary slackness. So what is this? What does complementary slackness say?
It's like the one where the lambdas, if they're so it's like if the inequalities are met, then the lambdas are not 0, and then if the lambdas are 0, then inequalities are not met, right?
Yes. Yes, it's something like that. You can precisely write it as lambda 1 star times the corresponding constraint, which was, let me go back, was f1x, right? How do you write it here? Minus x plus 1 equal to 0. So what does this mean? This means that if your lambda 1 star is not 0, that implies your x star should be equal to 1. Is that clear why? Because you want the product to be 0. So if your first term is non-zero, your second term must be 0.
Is it possible for both to be 0?
Yeah, both can be 0.
But it's not necessary, right?
Yes, but I think it's rare for both to be 0. Most of the times you get one non-zero or 1 0.
Okay.
So that's like an interpretation. If your lambdas are not 0, that implies your x satisfies your inequality with equality. Correct?
Yeah.
So that tells you something about which inequalities are like whether your x star lies in the boundary of your feasible set or not, based on this. So you'll see this interpretation later. when I say by boundary, if X star satisfies your inequality with equality, that means it lies in the boundary, right? Yeah, so I will like talk more about this in the later part of this question, which precisely brings about this concept. Lambda 2 star X star minus 2 is 0. For now, we're just writing down KT conditions. So how do you solve this now? So our goal is to like solve this for the lambda 1 star, lambda 2 star, and X star. So I'll just tell you like a general strategy I follow for doing this. So I always start out by looking at complementary slackness, because I find that this is the most useful to start out with. And in general, you start making assumptions about which lambda 1 stars are 0 and which lambda stars are like non-zero. So why does that help? So for instance, in this case, looking at the complementary slackness, suppose I assume lambda 1 star is positive and lambda 2 star is positive. That is, none of these lambdas are 0. Can such a set of lambdas satisfy KKT conditions? So this is a question I'm asking. Can we have lambda 1 star equal to lambda 2 star equal to 0? So can we have it?
Yes.
No, I should not answer
No.
that. Greater than 0.
Oh.
Lambda 1 star
No.
greater than 0, lambda 2 star greater than 0. So can we have this?
No.
No.
Yeah. Why? Because if you substitute lambda 1 star greater than 0, you get X star equal to 1. And if you also substitute lambda 2 star greater than 0, you get X star equal to 2. And X star can't be both 1 and 2 at the same time. Is that clear?
Yeah.
The strategy is to like make some assumptions and see if you reach a contradiction. So there are like 4 cases, right? So one case is both lambda 1 and lambda 2 star are non-zero. Your other case, this say was like case 1. Then your case 2 could be lambda 1 star is 0 and lambda 2 star is greater than 0. This is we saw like not possible. So next case to check is lambda 1 star is 0, lambda 2 star greater than 0. So the most useful, okay, so you make an assumption like this, and then the way to proceed is to like look at complementary slackness first. Why? Because if you assume lambda 2 star greater than 0, then you immediately get X star equal to 2, correct? So based on these like hints, and you try to solve these KKT conditions and check what assumptions on lambda 1 and lambda 2 will give you X star, lambda 1 star, lambda 2 star that satisfy all these KKT conditions. So you can take like 5 minutes to discuss this. This is like the most interesting part of this discussion. So I want to spend some time here. But this technique, which I talked about here, is very useful. And I think like this is one of the easiest ways to go about solving KKT. And invariably any other way will like some way or the other connect to this way. So is this technique clear to everyone?
Yeah.
Okay, so can you try and work out now, like what the KKT solutions would be?
Wait, can you explain why, like, what's the point of trying to solve the KKT conditions?
Oh, you want to solve KKT conditions because if a problem is convex and strong duality holds, then points that satisfy KKTs are your primal and dual optimum solutions.
So is there a unique KKT condition solution?
If there is a unique optimizers, then yes.
Oh, gotcha. Okay.
So in general, if your problem is convex, let me write this down. This is like useful. Change color because it's not related to this question, but useful in general. So if your problem is convex and you have X star, lambda star, mu star satisfy KKT, then it implies that X star is primal optimal, and your lambda star and U star. Okay, so the technical way to write this is not use star here and say, like, put something else here. Because you don't know a priori that they are optimal, but it turns out that they are optimal. So X tilde is primal optimal and lambda tilde and U tilde are dual optimal. And strong duality holds.
So this is useful when we don't know strong duality yet, but we want to.
Yes, so you can
find
always
if it
try to
does.
solve. You can always try to solve KKT, right? There's nothing stopping you from trying to solve KKT.
Mhm.
And you can always check if a problem is convex. So you try to solve KKT, and if your problem is convex, and you found some KKT solutions, then you know that you found the optimals. And the other way around is slightly more involved because you want. What is the other way around? Like we want to see if this is like, if this goes one way, like it goes this way. We want to see if it goes the other way around. But for that, you need something like Slater's to say that strong duality will hold. Because the other way says if X tilde, if X star primal optimal, lambda star nu star dual optimal, and strong duality holds. Okay, again, this is only for convex problems. Or equivalently, Slater's holds, then X star lambda star nu star satisfy KKT. So is that clear? So
Yeah,
to
but this one's
go,
not very useful.
yeah, which way is not?
The second way is, I'm saying the second implication that way, it's not very useful for us, right? Because
Yes, because if you
we
already
just care
found the, you already found the dual optimal and primal optimal, then you're pretty much done, right? You don't want to check KKT.
yeah.
Yeah. So this, the first way is one you'll usually solve, but yeah, the guarantee that such a solution will hold comes from your other way.
Yeah.
I have another quick question.
Yeah.
So just to make sure KET doesn't say anything about the uniqueness of the optimal solution. So there is it's possible that we can find more than one set of X star, lambda star, mu star.
Yeah.
Even though KET is satisfied.
Yeah. But if you see the next, if you see like in the, since the other way also holds, if you found multiple solutions to KKT and strong duality holds, then all of those solutions would be like primal and dual optimal.
Okay, got it. Thank you.
But if your problem is not convex, like weird things can happen. Like you can have lots of KKT solutions, but only one of them would be your optimizers.
Okay, thanks.
So if the first one's like if the problem's convex but KKT they don't, there's no KKT solution, then there's no strong duality. Is that true?
You can't say the other way around. Nope.
You can't say that. Okay.
Yeah. Because if there are cases, I think you will see a case where no point satisfies KKT, but strong duality holds. And why do such cases occur? It's mainly because so here we made an implicit assumption that your solutions exist, right? Like X star is primal optimal, but there are cases where your X star might not exist. For example, if you want to minimize, I consider this like minimize e raised to minus x subject to no constraint.
Oh yeah.
Okay, so the thing is like the X star here should be infinity, right? But you can't say something like star is infinity. So technically you would say that X star does not exist. So if, yeah, so such cases can result in not being able to find KKT solutions.
So
Okay,
if the problem's convex, sorry. Okay, so if the problem's convex but we can't find a solution to KKT, then how else do we go about like proving strong duality?
So you'll have to solve primal and dual separately without assuming strong duality holds. So you know how to find a minimum without using duality, right? Like we saw it
Yeah.
in some previous discussion and homework.
Yeah.
So you'll like solve the primal problem, and then you'll solve the dual problem, and then you'll check your optimal values in these two cases.
Yeah.
But then it's like not very useful to see if strong duality holds or not. Because the main advantage of using strong duality is like I will just solve the dual because it's like easier, and then I will say that, oh, I found solution to primal as well.
Okay, gotcha.
Okay. So why don't you solve this KKT condition now? Yeah, so here you can like share your work as you go. Again, this is like the most important part of this discussion. So I would encourage everyone to try and solve this on their own and like to discuss with each other.
So we know that x star must be equal to 2 if we're
For this
assuming
case, right?
that
Yeah.
lambda
I'm gonna
2
continue.
star is greater than 0, right?
Mm-hmm.
Okay.
So this implies x star is equal to 2. So what will I do next?
So next we want to solve for lambda 2 star. So we can plug lambda 1 and then x star into the stationarity condition.
Okay, very good. So you have 2x star minus, okay, what was it? Lambda 1 star plus lambda 2 star. Okay, 2x star minus lambda 1 star plus lambda 2 star is 0. That implies 2 minus, what is lambda 1 star? We assume it was 0 plus lambda 2 star is 0.
Wait, is it not 4 minus 0
Yeah,
plus?
sorry, yeah, 4.
Okay.
So what does that give you? Lambda 2 star is minus 4. Is this possible? Like, is this feasible?
No.
No.
No. Okay. Because it violates your dual feasibility condition. So what case remains now? 2 cases remain. So you will consider this, the case 3. Lambda 1 star is greater than 0. Lambda 2 star equal to 0. So what do you really get when you solve this case?
For this one, I got x star equals 1.
Mm-hmm.
And then
X star equals to 1.
from
This is
from
using
the
complementary slackness. Yeah.
and then from the gradient of Lagrangian, this
Mhm.
implies that lambda 1 equals 2.
Okay.
And this is
From
a
stationarity.
or from stationarity, yeah. And then this is fine.
Yeah,
Or
so
feasible? Yeah,
thus,
these points are feasible.
X star is 1. Lambda 1 star is 2. Lambda 2 star is 0. Satisfy KKT. Okay. So is everyone clear on how you got this? The technique is the same. You start with complementary slackness, make some assumption, then use it to get your X star. Then you use your stationarity condition to get your value of lambda 1 star. And then you will check if it satisfies primal and dual feasibility. And it turns out that for this case, it does satisfy primal and dual feasibility. And then you will go back here and use this. Problem is convex, and you found something which satisfies KKT. So you know that these are primal and dual optimum. And you're pretty much done. Is that clear?
Yes.
Yes.
Okay, great. So you can like look at the solutions. I think solutions are going to be the same. Let's just see. X1 star is 1, X star is 1, lambda 1 star is 2, lambda 2 star is 0, which is what we got. Okay, great. So these will be like put up later, or like, so you can look at them. So part D, Can you spot a connection between values of lambda 1 star, lambda 2 star in relation to whether the corresponding inequality constraints are strict or not at the optimal x star? So this is what I was like referring to before. So coming back, we have this complementary slackness, right? Here.
Yeah.
So what happens if your dual variable like lambda 1 star is strictly positive? It implies your inequality constraint will be satisfied with equality. Correct? So is this part clear? Why?
Wait, sorry, could you say that one more time?
So if your dual variable is strictly positive, that implies what lies in this bracket, which is the inequality constraint, will be satisfied with equality. Because what was this?
Yeah.
This was your inequality constraint. Like you had minus x plus 1 less than equal to 0. But then here, complementary slackness will give you minus x plus 1 is equal to 0.
Yep.
So if your dual variable corresponding to a constraint is positive, it implies that constraint is satisfied with equality. Is that clear?
Yes.
So now coming back to this picture, for us, okay, I want to draw this picture again. Our feasible region was this, right? X is 1, x is 2, and this inequality was like 1 minus x less than equal to 0, and we had like lambda 1 for this, and here you had x minus 2 less than equal to 0, and you had lambda 2 for this. So you saw lambda 1 star was 1, lambda 2 star was 0. So you can immediately figure out that your x would lie in this boundary. Clear?
Yeah. Wait, I think lambda 1 star was 2.
Oh yeah, 2. Okay. Doesn't matter. Just care whether it's positive or 0.
Yeah.
Okay, great. So this is the way to think about your constraints being tight or like satisfied with equality at optimum. And the way you can figure it out is by looking at the corresponding dual variables. Okay, so this was like a one-dimensional case, so not very interesting. But if you look at the second problem, I mean, this is also interesting, but second problem where you have like a two-dimensional optimization problem, then you will see more interesting things about your relationship between dual variables and lying on the boundary. Clear?
Mm-hmm.
Yeah.
Okay, great. Let's see what the solution says for this. Lambda 1 star is 0, corresponding equality satisfied with equality, and hence is not strict at x star is 1. Via lambda delta is 0, and corresponding equality is strict at x star is 1. Non-zero lambda 1 tells us, okay. So this thing about if you have a non-zero lambda, you can link your value, your lambda 2 star to like price of violating constraint, or like I should say reward. So for us, you had minimize x square subject to x greater than equal to 1, x less than equal to 2, correct? And you saw the constraint x greater than equal to 1 had lambda 1 star is 2, and x less than equal to 2 had constraint had dual variable lambda 2 star is 0. So what this says is, and the value of lambda 1 star is 2, I sort of approximately says that if I violate this constraint, let's say I take x equal to 1 minus epsilon, so I'm violating it by some amount epsilon, then I can decrease my value to something like x square minus 2 times epsilon. So this is your lambda 1 star. Okay, so this is not very precise because your objective is not linear, but in case your objective was linear, then this would be true exactly. But since our objective is quadratic, this is like approximately true. And I think there's a problem on like dual variable sensitivity in the current homework or like in the coming homework. So you will see more about this later. So is this clear on what happens when your lambda 1 star is positive? It says that if you violate constraint, you are rewarded. And if you like lie inside your feasible region, like you are penalized. Is this part clear?
So it's like if we shift x over from, because right now it's equal to 1 at optimality, but like if we shift it over to the right more, like we start getting rewarded by lambda 1 star, right?
Yes. It's like approximately because your objective function is quadratic. The thing is there will be like higher order epsilon terms here, which you have gotten rid of.
Okay. Oh, I see.
But,
Okay.
but it's just like the interpretation is that higher values of lambda 1 star would mean that small violations will give rise to large rewards. So is that clear?
Small.
So if your lambda 1, because you had lambda 1 star is 2, you could decrease it by 2 epsilon, right? But if your lambda 1 star was like 200, then the same violation would give you a much better decrease in your objective function.
So you're saying this pushes us to choose a better.
So the way this is useful is if you have like multiple such constraints and you had, let's say, some like extra freedom and you could decide which constraint to relax a bit.
Yeah.
So the constraint you would choose to relax would be the one which has your highest gain in terms of like how much you can decrease the objective function, and that is the constraint given by the largest value of dual variable.
Oh, okay, that makes sense.
That makes sense.
Okay, great. So we have 8 more minutes, so we can finish the next 2 parts. Find the dual function g lambda 1 lambda 2 so that the dual problem is given by this. So you want to find g of lambda 1 lambda 2. Again, this is just mechanical work. How do you find g of lambda 1 lambda 2? By definition, this is.
Oh, you min the Lagrangian over x.
Yes. So this part I will just like go over the solutions because this is something you have seen before. So it's written inf, but you can think of inf as min.
Yeah.
So min over x, Lagrangian Lx lambda 1 lambda 2. And going back to the Lagrangian, which we found here. Where did we find Lagrangian? Here. Is your Lagrangian convex in X?
Yes.
Is it convex? Answer is yes. You can check this by just taking second derivative. You can find the minimum by just taking the gradient and setting it to 0. And what happens when you do that? You get x is lambda 1 minus lambda 2 by 2. We just trust that the calculation is correct for now. And when you substitute this back, you get some dual function like minus lambda 2 minus lambda 1 whole square by 4 plus lambda 1 minus 2 lambda 2. Well and good. That's not very interesting here. It's just mechanical work. But what's interesting is the next part. You want to solve the dual problem in 2 for D star. Okay, so why is this useful? Okay, let me just, since we are like running slightly short on time, I'll give you the main ideas here, but you should like try to work this out on your own later. So the thing is, you know the dual function is concave in lambda, correct? Because we saw this proof in discussion before, you saw it probably in a homework. Dual function is always concave. And if something is concave, then I can try to find its maximum by just setting derivative with respect to lambda to 0. Is that clear?
Yeah.
Okay, so first step I would try is setting derivative to 0. Okay, then I can get like 3 cases. Okay, case 1, I find solution, and solution is, okay, I'm going to write it like this. Find solution lambda 1 star. I'm just going to write lambda star for generic dual variables, and lambda star greater than or equal to 0. Okay. I tried to set derivative to 0. I found some point, and that point was dual feasible. That means, like, I'm done. Everyone agreed on that?
Yes.
Yeah.
Okay, great. What else can happen? I find no solution. What does that mean? If you have no solution. So you saw something like this in the midterm, right? If you're trying to maximize a concave function and you found no solution, it usually means the maximum is infinity. Or like it always means the maximum is infinity. And you have to find the direction along which it goes to infinity. This means max is infinity. Okay, this is not strictly true. This is true as long as you're, at least you have one dual feasible point, then your maximum is infinity. There are some pathological cases, so we will not think about those. Max is infinity, and you can find direction along which it goes to infinity. Okay. And the last case, which is what will happen in this particular problem, is you find solution lambda star, but lambda star is not feasible. Okay, so in this last case, what will you do? Some ideas? What do you do if your unconstrained minimizer is not, maximizer is not feasible? Anyone?
Would you look at like the closest possible value on the boundary of your constraint?
Yeah. So you want to check boundaries. Okay.
All
And
right.
what are the boundaries here? The boundaries here are like lambda 1 star is 0 for this particular term, or lambda 2 star is 0. Correct? So in general, you can think of it in, I'm going to draw the two-dimensional case for this. So this is your entire two-dimensional plane. Let's say this is lambda 1, this is lambda 2 star, lambda 1 star. So the first case, like, you will try to find your maximum in this entire region. Use some, let's try to use some fancy stuff. I'm going to try to find this entire region, right? Okay, and let's say your maximum point was somewhere here. And you know this is not feasible, like not feasible. Okay, so then you can check on your boundary. So there are multiple boundaries to check, right? So you could check on this boundary. So your lambda 1 star was 0. And your lambda 2 star was anything, like anything on this line. I think I messed up. So lambda 2 star was 0 and lambda 1 star was anything. So you can check this boundary, but you might get like super unlucky and your maximum point could lie somewhere here. Okay, so this is again not feasible. So what will you do then? So again, you can, okay, so this is one condition that can happen. So there are other boundaries to check, right? So you could check this boundary. Your lambda 1 star was 0 and lambda 2 star was anything. Okay, and maybe now you got lucky and your thing lies here. So this is feasible. So if you find a feasible point, then you are done. Okay, but if you are unlucky even in this step and you found something like this here, not feasible, then we still haven't checked one thing. What have we not checked? We have checked We have not yet checked the case where both lambda 1 star and lambda 2 star are 0, which is like this point. So you will check this, and this better be, and this is feasible, and this will be your maximum. Is that clear on what can happen?
Yeah.
Okay, great. So you can work this out for this problem, and I don't remember which case exactly you will get, but you already know what your lambda 1 star and lambda 2 star, right? Because we solved it in a previous part of this question. But the main thing to take away from this problem is like this general technique of what happens when you try to maximize something by setting the derivative to 0 or gradient to 0. Like these three cases can happen, and most often you will encounter your case 3. This is like, in my experience, the most common case, but other two cases also show up. Like case 1 might show up, but it's like, it'll be like an easy question in the exam. Case 2 might show up, but it'll be like a super hard question in the exam. And case 3 would be like medium difficulty question in the exam. So you can think of it like that. Clear?
Mm-hmm.
Okay, so solution is given here. I'll also upload this to Piazza once I'm done with this. And okay, so part 2, same techniques apply to a different problem, which you have solved before by using this geometric interpretation with level sets. So it's a good exercise to try and solve this using KKT and duality framework now, and you should get the same answers. And yeah, that's pretty much it. Thanks everyone for coming. Hope you all have a good spring break. And I'll see you all 2 weeks from now.
Thank
Okay.
you.
Thank you.
It's finished.
All right. Yeah.
Thank you.
Bye-bye. So you can ask any questions now or in chat. I'll stay here for the next 5 minutes.
I have one question. So in general, we encounter constraint either in the primal or dual problem that we cannot satisfy. Are there any general systematic way to check which constraint we should satisfy first?
So the thing is, if you have something like a diagram, you can get some sense. The short answer is without cheating, no. What do I mean by cheating here? Is like if you get some intuition about how your level sets of the function looks like, you can get some ideas on which constraints are more important than others. And you can choose to make assumptions on lambda based on these observations. So if you look at solutions for question 2A, I think it will use some clever technique like this. But it's a very good question.
I see, because sometimes, like I just see that the unconstrained problem give us solution that cannot be satisfied.
Yeah. So in general, yeah, the short answer is here. Yeah, you would ideally have to like check all possibilities, but usually that's not necessary. You can make some like clever things, because as long as you find one, you're pretty much done, right? Like that's the hard part, like to find one.
I see. Thank you.
Okay. Any other questions? Okay, so if there are no other questions, I will stop the recording now.
All right. Thank you very much.